Okay, so by now I must have said the phrase direction of current over hundreds of times. And this might make you believe that current is a vector quantity because it has a value and a direction. But here I am trying to confuse you even more that current is actually a scalar quantity just like mass, charge, or voltage. So how is it possible? First off, what we intuitively think as the direction of current is actually the direction of current density. But saying it like, oh, it's just actually not a direction of current, but some other quantity called current density, blah, 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 isn't really a satisfactory answer to this question. So how do I convince you that current is indeed a scalar quantity? I'll accept that current is one of those quantities that feels like it should be a vector, but actually isn't. The reason we think that is because we learned the definition of vector is something that has both a value and a direction, and scalars are something that has just a value. But that's not the only difference. In fact, in some branches of science, vectors are not defined by directions. For a quantity to be called a vector, there are few other conditions that need to be made. One of them is that vector quantities need to follow the triangle rule of vector addition, which scalar quantities don't follow. Because scalar quantities are just numbers, so we add them up like just numbers. So this is a huge difference between scalars and vectors. And I think that would be the better way to distinguish between scalar and vector quantities to see how these quantities add up. Let's use that to figure out whether or not current is a scalar quantity. But first, let's go over vector addition for a second. We all know that displacement is a vector quantity. Why? Because say you walk from point A to point B, which is just 4 meters away in the x direction. Then walk from point B to point C, which is 3 meters away in the y direction. So now how much do you need to walk to achieve the same effect? You don't need to move 4 plus 3 equals 7 meters. You just have to walk 5 meters in this diagonal direction to reach the point from A to C. So that means you can't just add up 4 and 3 to get the total displacement. Rather, we need to figure out what's the length of the unknown side of this triangle. This is called the triangle law of vector addition. Since displacement follows this law, it is a vector quantity. Now the question is, does current follow this law of vector addition? Let's take water current as our example. Say there are two water pipes through which 4 kg and 3 kg of water is being delivered every second. Now, if we connect them, how much water will be delivered every second? If the rate of water flow was a vector quantity, they would look something like this. And if you added them up, following the laws of vector addition, you will get 5 kg of water flowing every second. But is that really what happens though? Let's represent each kilograms of water flowing through the pipes every second as one ball of water. Then we will see that 4 balls of water is flowing every second from left to right. And 3 balls of water is flowing upwards every second. And now you can immediately see that the total there should be 7 balls of water flowing through the final pipe. That means water current doesn't follow vector addition, rather they follow simple scalar addition. And that in turn means that water current can be a vector quantity, it must be a scalar quantity. The same logic applies to electrical systems as well. If you had 4 coulombs of charge flowing every second from the left pipe, that is 4 amperes of current, and had a 3 amperes of current from the lower pipe, you would have a total of 4 plus 3, 7 amperes of current going through the remaining pipe, because these charges have no other way to go. So electric current also follows simple scalar addition instead of vector addition, which means electric current is definitely not a vector quantity, rather it's a scalar quantity. So now you definitely know why it's not a vector. By the way, just as a teaser, the idea we use here, that is, you can add up other currents to figure out the remaining current, is actually a well-established law of electricity called Kirchhoff's current law. In the future, we will come back to this scenario again. But that's it for today. See you in the next lecture.